Welcome to this video. In this video we will find the Thevenin equivalent circuit of a simple circuit with one independent source. So the circuit that we will find the Thevenin equivalent of is on the left. You can see there's one independent source, and on the right I've shown the structure of the Thevenin equivalent circuit. So what we need to do to find this Thevenin equivalent circuit is to find VOC, which is the open circuit voltage, and RTH, which is the equivalent Thevenin resistance. So we'll go ahead and get started trying to find the open circuit voltage. So the open circuit voltage is the voltage at the two terminals of the circuit without anything connected to those terminals. So what I've drawn here is the open circuit voltage. And so we look at this circuit and we say, well, I do have a single loop here, so that seems like that would be helpful. The one thing that seems a little strange is it may not be clear what to do with this 1 k ohm resistor which is sitting here. And basically it turns out that this 1 k ohm resistor doesn't affect VOC in the following sense. Basically, this end of the resistor is not connected to anything. So there's no way for current to flow through the resistor. It just won't happen. So there's no current through the resistor, again because this end's not connected to anything, which means that there's no other place for there's no place for the current to flow after it goes through the resistor. If there's no current flowing through the resistor, then the voltage across the resistor is 0 volts. Which means that the open circuit voltage that I want to find is actually the voltage across this 1 k ohm resistor. Okay, again, because the voltage across this 1 k ohm resistor is 0, so that means that this point is at the same voltage as this point. So I need to find VOC. In this case it's going to be pretty easy. I have VOC is equal to, I can use a voltage divider because I have this 8 volt source in series with a 2 k ohm resistor and a 1 k ohm resistor. So it's going to be 8 volts times 1 k ohm over 1 k ohm plus 2 k ohms, which turns out to be 8/3 volts, which I guess if I wanted to write this in decimal form, this is 2.667 volts. Have I got that right? Yeah, I think I've got that right. So we're halfway there in the sense that we now know what the open circuit voltage is. Now what I need to do is find the short circuit current. And to do that, let's tidy up a little bit. I'll get rid of this guy, get rid of this guy. Okay, so now I need to find the short circuit current. I do that by shorting the two output terminals. And the current that flows here will be ISC. Okay, so let's see, how can I do this analysis? Well, it looks to me like I have two 1 k ohm resistors, this guy and this guy, in parallel. So I could take the parallel combination of this guy and use that then to find the voltage across these two resistors. And once I've got that voltage, then I can find the short circuit current. You'll notice the short circuit current is the same as the current that flows through this 1 k ohm resistor. Now, one thing I want to warn you about, because it's a mistake that I've seen almost everybody make at some point, your temptation is to use this VOC that you've already computed somewhere in the computation of ISC. You can't do that because by shorting the terminals here, I've changed the circuit. No longer do I have a circuit that has nothing between the top terminal and the bottom terminal. Now I have a circuit that has a short between those two terminals. So this VOC that you computed, you have to remember this is for a completely different circuit. Okay, well, to now solve this using the approach that we've just talked about, suppose I call the voltage between here and here V1, and I need to find that. Once I find V1, I know the voltage from here to here, which tells me what the current would be. So to do that, I will do the following. So we have 2k ohms. Now this 2k ohms will be in series with the parallel combination of the 1k ohms. And if I have two 1k ohms in parallel, then the equivalent resistance is 500 ohms. Okay, and again, this voltage here is still V1. I haven't combined V1 or hidden V1 inside the equivalent resistance. So I can say then that V1 is, using the voltage divider, 8 volts times 500 ohms over 2k ohms plus 500 ohms, which in this case is going to be 8/5, which I can write as 1.6 volts. And then I want ISC, and as I said, ISC is the voltage across the 1k ohm resistor across this guy. So that's going to be 1.6 volts divided by 1k ohms, which is then 1.6 milliamps. Okay, so we have the open circuit voltage, which we got here. We now have the short circuit current, which we have here. So we can find the Thevenin equivalent resistance as, let's see, we'll do it up here. RTH is 2.667 volts over 1.6 milliamps, which when I work this out should be equal to, well, let's see what it is when we work it out. It turns out to be 1.667 k ohms. Okay, so this is good. I basically have the open circuit voltage that I needed and the Thevenin equivalent resistance. Now, normally we would say we're done, but I'd like to show you that there's an alternative way that we can compute the Thevenin equivalent resistance for this circuit. This circuit has no dependent sources. So let me clean up just a little bit here. So what I can do then is, rather than finding VOC over ISC, because the circuit has no dependent sources, I can look at this terminal and find the equivalent resistance between them. So if I look at this terminal, I have, well, let me back up. Before I can do that, I need to set all of my sources to 0. And so to set a voltage source to 0, we replace it by a short circuit. Okay, now we can do what we need to do. You'll notice that this 2k ohm resistor and this 1k ohm resistor are in parallel. So I can replace this 2k ohm and 1k ohm resistor with the following: 1k ohm times 2k ohms over 1k ohm plus 2k ohms, which should be 667 ohms. So now I can replace my parallel resistances by 667 ohms, I still have this 1k ohm here, and this goes here to my terminals. Okay, now I have a 1k ohm in series with 667, which basically says then that my Thevenin equivalent is going to be the equivalent of these series resistors, which is 1.667 k ohms, which turns out to be the same answer that we got when we did it by finding the open circuit voltage and dividing by the short circuit current. It's always kind of refreshing when these things work the way they're supposed to. So that pretty much concludes this example. The idea, again, is that I could take my original circuit and I can replace it now by, well, in fact, let's tidy up to summarize. I can replace it by a single source, which is 2.667 volts. This is my open circuit voltage, and a single resistor, which is 1.667 k ohms. And this is electrically equivalent to my original network. Okay, with that, we will end this example. Thanks for watching.